Welcome back, everyone. Uh, this is the second episode of our fraud detection model series. So, in our last episode, we cracked open a healthcare fraud ring using pure graph intuition. Today, we go a little deeper. We are going to learn the math, the vocabulary, and the architecture that allows a machine to see what we saw and do it at a scale no human analyst ever could. We will even get our hands dirty with some Python. Let's get to it. Get into it. Before we dive in, let's orient ourselves within the bigger picture of this series. In episode 1, we visualized a healthcare fraud network and relied on visual intuition. We spotted suspicious clusters of patients and providers and said, that looks wrong. And it worked, but intuition doesn't scale. You can't hire enough analysts to manually eyeball millions of Medicare claims every month. So in this episode, we are building the foundation, the mathematical language of graphs, the vocabulary every data scientist needs, and an intuition for how graph neural networks actually think. We'll also write a small Python code to put it all together. And in the next coming episode, we will build a real end-to-end fraud detection model using any recent machine learning or deep learning models. So everything today sets the stage for that. Think of this episode as learning the grammar before we write the novel. Let's go back to where we left off. Do you remember that suspicious provider from episode 1? Dozens of patients all filing claims through the same entity. Individually, every single claim looked perfectly normal. The right diagnosis code, a plausible procedure, a reasonable amount. Nothing would raise a red flag in isolation. But the moment you zoom out and look at the network, the pattern becomes impossible to ignore. That provider is at the center of a web connected to patients who are also connected to each other in ways that don't make clinical sense. And that brings us to the two questions driving everything in this episode. First, how do we mathematically represent this network so that a machine can see what we see? Second, why did traditional machine learning completely missing these kind of patterns? The answer to both questions comes down to one insight: fraud is not an isolated event. It is a relational phenomenon. It lives in the connections between actors, and to detect it, we first need to master the language of graphs. Every graph, no matter how complex, is built from just two fundamental ingredients: nodes and edges. Everything else is built on top of these two concepts. Nodes represents entities, the actors in our story. In healthcare fraud, our nodes are patients, providers, insurance, and even more entities that we need to like explore, do research, and uh, join it together. One such is entity that we saw in the last episode is the attorney's role, which plays a significant part in many real-world fraud cases. It is often missing from publicly available datasets. That's a gap with real implications for research and something we will acknowledge when we talk about limitations. Edges represents relationships between those entities. In uh, healthcare, edges encode insurance claims being filed, financial transactions flowing between parties, referrals from one provider to another, and patterns of service interactions. And then there is a third element that makes graphs truly powerful for machine learning, that are features or attributes. These are behavioral signals attached to our nodes. Things like how frequently a provider submits claims, what diagnosis codes they favor, or a patient's reimbursement history. Nodes, edges, and features. These are the building blocks. Keep these in mind as we move forward. Now, not all graphs are the same, and choosing the right type of graph is one of the most consequential decisions you will make as a data scientist or AI engineer. A homogeneous graph has only one type of node and one type of edge. Imagine a social network where every node is a person and every edge is a friendship. Clean and simple, but limited. But on the other hand, an heterogeneous graph allows for multiple types of nodes and multiple types of edges. And this is where healthcare fraud analysis truly lives. In our fraud network, a patient is fundamentally different from a provider, which is different from an insurer, which is also different from attorney's role. The way they behave, the features that describe them and the relationships they have are all semantically distinct. A homogeneous model would flatten all of this richness into a single layer, and in doing so, it would erase the very signals that scream fraud. Real healthcare fraud networks are inherently heterogeneous. To model them accurately, we need a graph structure that honors the complexity. Here's the uncomfortable truth that most data science pipelines haven't caught up to yet. The way most healthcare data is delivered to us is a flat tables. Rows of claims, columns of attributes, patient ID, diagnosis code, procedure code, reimbursement amount. Each row sits independently, disconnected from every other row, and there is nothing inherently wrong with that format. It captures what happened. But here's the problem, it doesn't capture who conspired. Let me make that concrete. In a tabular dataset, you might notice that provider X submitted a lot of claims, but you can't see that those 50 claims all happened in 30 days. That the patients share identical diagnosis codes, that two of those patients are also connected to a second suspicious provider, and that the final financial flows between insurer and provider follow an unusual pattern. That's the whole picture. The network reality is invisible in a flat table. Structured data captures the rows, graph captures the web, and fraud lives in the web. So what happens next? When you throw a standard neural networks at this problem, even a deep one, it fails. And here's precisely why. Traditional neural networks are built on a core assumption that data samples are independent and identically distributed. In plain English, they assume that each row in your data set has nothing to do with any other row. That assumption is catastrophically wrong for fraud detection. First, that's an assumption mismatch. A claim that looks normal in isolation becomes highly suspicious when it's surrounded by 47 identical claims from the same provider. A standard model can never make that connection. Second, there is a lost context. When you train on tabular data, the provider patient insurer triangle disappears entirely and the model is left blind to collusion signals. The third, perhaps most critically, standard models have no propagation mechanism. If one provider is flagged as suspicious, their neighboring patients and associated insurers should inherit elevated risk. A GNN, graph neural network, can do this naturally. A tabular model simply cannot do it. Let me make this viscerally concrete with a thought experiment. A provider bills $3,200 for a procedure on a Medicare patient. You look at that single row in your spreadsheet, completely normal, nothing unusual. Your standard model gives it a low fraud probability and moves on. Now zoom out. That same provider has billed the exact same procedure, $3,200, the same diagnosis code, the same procedure code for 60 patients this month, in a particular month. All of them identical. That's not medicine, that's a fraud ring. This is exactly the difference between looking at data in isolation versus looking at in context. A graph preserves that context. It keeps the connections alive. And a model trained on graph structure can learn to recognize this pattern automatically. Context is everything, and graphs are the only data structure that keeps context intact. So now we are ready for the main event. What is a graph neural network and why is it the right tool for this job? A graph neural network is a deep learning architecture specifically designed to operate on graph structured data. Instead of processing isolated rows, it learns by passing information between connected nodes. That single design choice changes everything. Here's the core principle. A node's representation is shaped by both its own features and the features of its neighbors. And this is refined iteratively through what's called message passing. We will go deeper on that in just a moment, maybe in the next coming slides. Now, why does this work so well for fraud? Because fraudulent actors leave traces in their connections. A fraudulent provider doesn't just have suspicious claim amounts, they have suspicious relationships. GNNs, that is graph neural networks, learn to recognize these relational fingerprints that tabular models simply cannot see. The output of a GNN is a rich embedding, a vector for each node that encodes not just its own attributes, but the entire behavioral context of its neighborhood. That embedding becomes the input to your fraud classifier. Message passing, right? Which is the mechanism that makes GNNs work, and it's worth taking a moment to really internalize it. Here's the cycle. Every node in the graph aggregates messages from its neighbors. It then combines those messages with its own features. It updates its own representation based on this combined information, and then it propagates its updated representation back to its neighbors for next round. You run this cycle multiple times, multiple layers, and after just 2 or 3 rounds, each node has effectively absorbed information from its entire local neighborhood. Let's put this in fraud terms. Take a patient node. In the first round, it receives information from its provider. In the second round, it receives information from the provider's other patients and the insurer. After a few rounds, that patient's embedding encodes a full suspicious neighborhood context. It knows in a sense who else its provider has been billing. One key hyperparameter here is the number of message passing layers. More layers means that node can see further into the graph. But too many layers leads to over smoothing as well, where all nodes begin to look at the same because they have absorbed too much of the global graph. It is a balance and it's one of the key tuning decisions in GNN design. Let's look at 3 specific GNN architectures that have shown strong performance in healthcare fraud detection research, each offering a different strategy for learning from graph structure. The first is GraphSAGE, sample and aggregate. Instead of using the entire neighborhood, GraphSAGE samples a fixed number of neighbors during each aggregation step. This is critically important for real healthcare claims networks that have millions of nodes and edges. GraphSAGE makes GNN training scalable. The second is Re-GraphSAGE, a relation-aware extension. It goes further by distinguishing between different types of edges when aggregating. An insurance claim edge carries different information than a referral edge or a payment edge. Re-GraphSAGE preserves that semantic distinction, allowing the model to learn more nuanced fraud signals. The third is the hybrid GNN. This architecture combines GNN-based relational learning with traditional tabular ML features, the best of both worlds. You get the graph level context from the GNN and you keep the structured data signals from classical features. In practice, this hybrid approach often yields the strongest fraud detection performance. Each of these represents a different trade-off between scalability, expressiveness, and interpretability, and knowing when to use which is part of the craft. In the heterogeneous graph, different node types are processed through different channels. A patient node and a provider node don't just have different features. They have different learned representations, different update mechanisms, and different roles in the overall graph structure. The mechanism that handles this is called multi-graph attention mechanism. It allows the model to learn which channel to trust for each specific prediction. For detecting a patient who's part of a billing ring, Maybe the provider to patient channel carries the most signal. For detecting an insurer complicit in fraud, the financial transaction channel might dominate. This dynamic channel over aggregation is what makes heterogeneous GNNs so much more expressive than their homogeneous counterparts and so much better suited to the complex multi-actor reality of healthcare fraud. This is one of my favorite concepts, I would say, in the entire field, and I think it will click for you immediately. A meta path, which is a sequence of node types connected by edge types that defines a meaningful indirect relationship. Think of it as the grammar of heterogeneous graphs, rules that tells us how entities relate to each other beyond direct connections. Let me walk through three that are directly relevant to fraud detection. The first is patient-provider relation, which is a direct claim relationship. Simple, a patient received services from a provider. Next is provider to provider, which captures a co-billing relationship. Two providers who are both submitting claims for the same patients. One on its own, this might be innocent, but at scale, it becomes a strong signal worth investigating. And here's the powerful one, patient-provider-patient relationship. This two-hop meta-path captures indirect patient similarity. Two patients who share a suspicious provider. This is the classic fraud ring signature. Those two patients may have never met, may live in different cities, but they are structurally connected through the provider who is billing them both for identical procedures. Metapath allows a GNN to reason about second order and third order relationships where connections completely invisible in tabular data but that scream fraud the moment you see them in a graph. Here is another dimension we haven't addressed yet. That is the time, the temporal information. Sophisticated fraud rings don't stay static. They adapt. They rotate providers, switch billing codes, and gradually ramp up claim volumes to avoid triggering sudden statistical anomalies. Catching them requires not just understanding the graph structure at a single moment, but tracking how that structure evolves over time. This is where spatiotemporal GNNs come in. And spatiotemporal GNN has two components working together. One is GNN layers that captures the spatial graph structure and LSTM or transformer layers that captures how the structure changes temporally. The combination is especially powerful for detecting slow burn fraud. Schemes that unfold gradually over months and are specifically designed to look normal at any given point of time. Let me give you a concrete example. A provider gradually increases their claim volume over 6 months while rotating patient IDs every few weeks. A static GNN sees only a snapshot and misses it entirely. And spatiotemporal GNN sees the trajectory and flags the anomalous sustained growth pattern for investigation. So I will show you this building this graph at the end of that session. So now we will move on to the next thing, okay, which is to graph centrality, finding the hubs. So maybe you need a little more, you'll understand more when we actually build that small graph for a visualization of that graph representation and the centrality measures of that graph. Okay, but let's go one level deeper on centrality because it's one of the most practically useful tools in the graph analysis toolkit. Degree centrality is the simplest. It counts connections. A provider with an unusually high degree, many patients flowing to them is an immediate red flag. It doesn't prove fraud, but it tells you exactly where to look first. Betweenness centrality asks a more subtle question. How often does this node sit on the shortest path between other nodes in the graph? A high betweenness node is acting as a broker, a connector sitting between other actors, coordinating or facilitating their interactions in a fraud ring. That's your organizer. And finally, the page rank. The same algorithm that originally powered Google search. Use higher scores to nodes that are connected to other important nodes. In fraud terms, a provider connected to other already suspicious entities inherits elevated risk. Suspicion propagates through the network, and all of these scales, right? Graph databases like Neo4j can compute these measures across billions of nodes and edges, making real-time enterprise scale fraud detection genuinely feasible in production. Now, good science means being honest about where the gaps are. Graph neural networks are powerful tools, but they come with real challenges that we shouldn't gloss over. One is the data limitations. This is the first practical obstacle. Most publicly available healthcare data sets arrive as flat structured tables. Building rich labeled graph data sets requires significant domain expertise, careful data engineering, and often collaboration with actual fraud investigators. And second is the missing attorney entity, which is a specific but important gap. In many real-world fraud schemes, an attorney plays a central coordinating role, yet this entity is largely absent from available datasets. That's a genuine blind spot that weakens detection models in ways that are hard to quantify. And third is the heterogeneous complexity, which is a real technical challenge. Multi-type graphs with multi-channel attention are powerful, but they are also significantly harder to design, tune, and interpret. Deep expertise and computational resources are required. And finally, scalability. Full graph GNN training on national Medicare data with millions of claims and nodes is computationally expensive. Mini batch strategies like GraphSAGE help, but scalability remains an active area of research and engineering. Naming these gaps isn't pessimism, it's a mark of rigorous practitioner. And yet, despite these challenges, graph-based fraud detection is one of the most exciting frontiers in applied AI today. The opportunities ahead are both technically fascinating and genuinely impactful. Multimodal graphs represent the next frontier in data richness, combining structured claims data with unstructured text like clinical notes, discharge summaries into a unified graph representation. The signals hidden in either modality alone become far more powerful when combined. Explainable GNNs address a critical real-world requirement. Regulators and compliance teams need to understand why a claim was flagged, not just that it was flagged. Explainable GNNs provide subgraph level explanations that make model decisions auditable and legally defensible. Real-time detection is where the financial stakes are highest. Streaming GNN architectures that process claims as they arrive, flagging frauds in seconds, could stop payments before money leaves the system rather than trying to recover it after that fact. And finally, the enterprise knowledge graphs, which represent the vision at scale, integrating GNN models with Neo4j style knowledge graphs at the payer enterprise level, enabling continuous fraud intelligence across billions of transactions. The path from today's foundation to tomorrow's applications is shorter than you might think. Let's take a moment to zoom out and appreciate how much ground we have covered today. We started with graph vocabulary, nodes, edges, and features, or attributes, the building blocks of everything that followed. We built the case for why GNNs are the right tool, message passing, neighborhood aggregation, and learning embeddings that encode relational context. We explored advanced methods like GraphSAGE for scalability, Re-GraphSAGE for relational awareness, MetaPaths for semantic reasoning, and spatiotemporal GNNs for fraud that evolves over time. And we brought it all to life with an hands-on like Python code, Jupyter notebook that I will show you. Building a real claim graph and surfacing suspicious nodes with centrality measures with some base level understanding. So there are three key ideas to walk away with. Graphs are the language of relationships. They preserve what flat tables destroy: context, connection, and collusion patterns. GNNs learn from connections. Message passing transforms raw graph structure into rich behaviorally informed node embeddings. Python is your starting point. You now have working code to build, visualize, and analyze a claim graph. That's the foundation for everything in our next coming episodes. So in the next episode, like we move from vocabulary to engineering, we are going to build a real healthcare fraud detection model. So here I mentioned as PyTorch geometric. We can also try with some other very recent technologies, right? So for better understanding, I just put PyTorch geometric. So which is one of the GNN pipeline that we need to set up to build the model and train the model. So that's why I kept PyTorch geometric here. So this is this PyTorch geometric pulling in actual CMS Medicare claims data, constructing the heterogeneous graphs from scratch, training a GNN, evaluating it, and interpreting the results. Which providers does the model flag, why, and how do you know if it is actually working? We will answer all of that, and everything we covered in episode 1 and 2 comes together. If you haven't already gone through my previous episode, please go through it. Drop your questions and comments, and I read every one of them and they shape future episodes. Thank you so much for spending this time with me. I'll see you in the next episode. Thank you.